Hello, my name is Junyoung Yang of Machine Learning and Intelligence Lab of KAIST, and I'm going to introduce our work, Attribution Preservation in Network Compression for Reliable Network Interpretation. Recently, there has been a demand for deep neural networks in safety-critical applications such as autonomous driving and wearable health monitors. To be considered safe in these fields, first, they need to be reliable in the sense that there should be no temporary lapse in service, which means that constant service must be rendered. However, cloud-based DNNs are affected by internet connection quality, so the networks must be directly embedded in edge devices to provide constant service. To this end, network compression is employed to reduce the size of the DNNs to be fit into the edge devices. Second, they must be trustworthy, as in providing reasons and interpretations to its decisions for humans to understand. To do this, explainable AI algorithms are employed to do this. Network compression, such as pruning and distillation, shrinks the network's size to consume less computation while maintaining its predictive power. Explainable AI methods produce human understandable interpretations of neural network outputs. The most widely used method is input attribution. In the surface, these two techniques seems unrelated. However, through experiments, we discovered that compressing a network causes the attribution map of the network to deform or even break down. This is because only simple prediction performance metric is considered when compressing the neural network. Since this phenomenon occurs in all kinds of compression and attribution methods, it becomes a detrimental safety vulnerability when using both technologies at the same time. To address this problem, we propose a simple and yet effective framework to preserve attributions. The idea is to promote the attribution map of the compressed neural network to follow the map prior to its compression. To achieve this, we employ a matching regularization loss while compressing to keep the attribution maps of the compressing network closer to its former self. We formulate the attribution maps by collapsing the feature map in the channel dimension. We propose two methods to do this. The first is to give equal importance to all channels, and the second is to set the importance weights as the gradient sum of the weights within each channel for the model prediction, reflecting the importance of each channel in the attribution map. In addition, by dropping the channels probabilistically before the transfer, we reduce the overfitting of the attribution map. Next, we conducted experiments on the effectiveness of our method. Experiments on network distillation confirmed that the compression process indeed damaged the attribution map. With our method employed, the attribution maps were preserved when compared with the pre-compression attribution map and the ground truth segmentation. We also discovered that preserving attribution helps in preserving the predictive performance as well. For unstructured pruning, the results were similar to distillation. Attribution scores and predictive performance were preserved. Finally, we obtained results on structured pruning, which showed similar tendencies. These images are such examples of deformed and preserved attribution maps. If you look at the second column, before compression, the neural network is focusing on where the object is, but when it's compressed in the third column, you can see that the attribution map is broken. Finally, looking at the last column, we can see that using our method, the attribution map is kept close from the original. Next, we will move on to the tutorial code repository. First, we will give an overview. You can access the repository by visiting the link here. The tutorial code is written in Python and PyTorch. You need to configure your development environment to meet the requirements listed. The repository contents are as follows. We have directories of codes for 3 compression methods: distillation, unstructured pruning, and structured pruning. The explain directory is for the codes of attribution algorithms. Evaluate pred and evaluate localization is for the evaluation of the compressed networks. In this tutorial, we will use the Pascal VOC 2012 dataset. This dataset is a multi-label classification dataset with 5,717 training and 5,823 validation samples. From the validation set, we held out 1,449 samples that possess segmentation masks to use as a test set. The actual input to the model is as follows: a 4-dimensional RGB image tensor of height and width of 227 pixels. The labels are provided as a 2-dimensional tensor, which is in a form of multi-hot coding. There are 20 kinds of labels in total. To run the experiments, first you need to download the dataset and place it in the right directory. Download the dataset and extract it by following the instructions in the repository. If it's successful, then the shell log should look like something like this. Next, we train the original model that we will try to compress. To train this, we will run the voc vanilla main.py script. Run the script with appropriate arguments as detailed in the repository README file. If the training script executes normally, then the shell log should look something like this. Next, we compress the original model trained in the last slide with attribution matching enabled. Here, we will demonstrate with knowledge distillation. To run this experiment, run the voc distill main.python script with arguments described in the repository. If the training script executes normally, your shell log should look like the following. Finally, after we are done with compression, we can finally evaluate the compressed model. With evaluate_pred.py, we can evaluate the prediction performance of the compressed model. Please refer to the repository README for arguments. With evaluate_localization script, we can evaluate the localization and segmentation performance of the attribution maps produced by the compressed model with respect to the ground truth segmentation masks. This is the end of our presentation. Thank you for listening.